So how's everybody doing today? Glad you all could make it out here, have some fun. So we had this wonderful talk about rocketry, all this stuff about getting into space, just figuring out what the universe might be like. So I'm going to give us a bit of a talk that's focusing more on what's actually going on in space and seeing what kind of science we can understand from that. So as she mentioned before, I'm Kai. I work with Dr. Elizabeth Mills. She's a part of the Nearby Galaxy Lab, which studies our galactic center, basically this big, dense region of gas in the center of our galaxy. So let's get into this a little bit. So first things first, let's go over a bit of what I'm going to talk about. So I'm going to first define the region that I'm looking at, this region of the center of our galaxy, this extremely dense, active area with interesting organic chemistry. And I'm going to give a brief little chemistry review for everybody, just so we all are on the same page and where we're going. Afterwards, we'll talk about and use that chemistry to discuss how molecules and organic structures can form in space. And going off of that, I'll then talk a bit about how I actually collect this data. We'll look into the actual data and talk about what kind of organics can form and how that can relate to the origins of life. And most interestingly, I'll give a large segment talking about why anybody should really care and like what's important about it. Because I mean, I can't just like shout to you guys a wall of information, expect you to care. We need reasons to do this, right? So let's see what happens. First things first, let's go on a bit of a trip. So right now we're here at the Cosmosphere in Hutchinson, Kansas. So we're going to start there, and we're going to zoom out. So as you guys can see, this is Earth. Overlooking it, we just need to zoom out and look further. But the region I'm looking at isn't on Earth, it's out in space. But how far in space? Well, let's zoom out again. So now we're starting to look at more of the solar system. I recommend you look at some of the side TVs, it's a little dim. But now we're looking at our solar system. The thing is, we're still not far enough. This isn't even a parsec away. So now we're going to zoom out again. And now, again, looking at the side screens, we're going to zoom all the way out to look at our galaxy, the Milky Way galaxy as a whole. And that's where we are, that little dense region. And we're going to travel all the way to that big, bright bar in the center, known as the galactic center. This is about 25,000 light years away from where we are now. Very, very far away. This region of the galactic center is extremely dense. It's one of the densest regions known anywhere in space, and because of that, it's extremely dynamic. It's an active region. It's super hot, there's a lot of chemistry happening there, and it's got a lot of interesting stuff going on. But strangely, there's actually not a lot of star formation here. You'd think that if there's a lot of stuff in space in an area, it'd form stars, but this area actually doesn't really form that much, which is a curiosity that has caused scientists to look at it for a pretty long time. But let's take a bit of a step back before we get too in-depth into like what we're looking at exactly and talk about chemistry and give everybody a good review on like what's going on with that. So space is full of gas or stardust, and that gas is not just sitting there empty, it's dynamic. It's in a constant equilibrium where it reacts with itself, forming different kinds of molecules at all times. And that gas is moving, it's forming stars, it can collapse into black holes, it can just move at very high velocities. It's very, very active. And when it does this, it gets excited, it gets energetic. And that energy results in the emission of photons or light. Just like the stuff coming from our ceiling lights, it emits it and we're able to pick that up. And I study that emitted light and use that to understand what's going on in a local environment. I use that to understand its chemistry. So let's do a bit of a brief overview of chemistry. And I know this looks a little scary, but hopefully we don't jump it out at you too much. But let's discuss specifically combustion, a pretty common reaction that everybody's been exposed to. For example, something with a lighter. You have an input energy for an exothermic reaction. If you look down here on the bottom right, you see that there's two molecules starting at a common energy state. And they need to be given a little push, a bit of energy to let them react. And afterwards, the energy drops off drastically. And you're letting something like that butane up there react with carbon or react with oxygen to form CO2 and water. And in that case, you can get a lighter and form fire. And because of that, it's able to release a lot of heat. This state is a lot more stable, there's a lot more molecules being produced, and because of that, it releases heat. And that heat just gets dumped into the atmosphere. I could run this all day, and it'd mildly heat the area around me. However, there's a problem. Space isn't much like the rest of the world. Space is pretty empty, and because of that, there's nowhere for it to actually dump any of that energy. It doesn't really have anywhere to go. And what do I mean by that? Because I just told you that there's dust in space. So what do I mean by empty? Well, our atmosphere has about 10 to the 25th molecules per cubic meter. And space, this dense region, the densest region I just told you about, only has about 10 to the 12th meters. That's 10 trillion times less dense. When I say there's nothing there, there's basically nothing there. But I just told you that there's chemistry happening. So how can this chemistry happen if there's nowhere for this energy to go? You would normally have molecules react, and then they'd emit heat. But if they can't emit that heat, they're just going to radiate apart again like the reaction never happened at all. So what on earth is going on here? Why are there reactions in space? Well, that's because reactions in space cheat. So we're going to go over a few basic things that you need to know about astrochemistry. First, we need to talk about how they're catalyzed. Before I mentioned a lighter, there's that little bit of flint that sparks, and that gives that activation energy to then light the lighter. Well, reactions in space need the same thing. They need a little push to let them interact with one another. So you have stars, massive energetic things in space that are emitting a ton of radiation, light, energy, even cosmic rays. And this stuff provides that push. It excites molecules and it causes them to start reacting with one another. So the first thing we need if we want to see chemistry is we need activity, so we need star formation. The second thing we need is something called dust grains, and I'll get into what those are in just a minute. So let's take a pretty simple reaction, just two hydrogen atoms that are charged and energetic. They interact with one another, and they're able to form H2 and H3. H3 is then able to react with a carbon atom, and that carbon lets it form these structures where you're just basically putting more and more hydrogen onto a carbon atom until you form something like methane, which is just CH4. Now, let's throw an oxygen atom in there. Well, guess what? That CH3 is able to actually bond to the carbon and form HCO and eventually carbon monoxide, which is a molecule I'm sure many of you have already heard about. This is actually one of the most common molecules observed anywhere in space. And this is one of the few reactions that can actually happen just naturally because the change in energy is so small, it's actually able to emit all of it as light or vibrational excitation. So this can happen without any help. But if you want to get anything more complicated than that, you need what are known as dust grains. Basically, these big pieces of ice that are just floating in space. There's billions upon billions of them in a region, and they're consisting of all kinds of different molecules like water, methane, CO2, and they all just exist as this block of ice. And what will happen is you'll get a molecule like that carbon monoxide, if I can get this laser to work. It'll bond onto the dust grains, and then as it just like collides with it, it sticks to it. And then you have all these other molecules just sitting on the dust grain, and they actually start to interact with one another. And because there's somewhere to actually dump that energy now, they'll bond and they'll react. You'll get a CO bonding to like one of these CH3s. They connect together, and they're able to dump their energy into the ice grain. And that energy is actually enough to then kick the molecule off of the ice grain and let it just start floating in space. So again, you get something like carbon monoxide. You have hydrogens and carbons just existing on the surface of this. They bond dynamically just by existing around that area and being heated by a star. And then after they bond, they add together and then dump all their energy into the ice grain and kick themselves off into space. And that's how you can form something like dimethyl ether. And this is happening all over space with all different kinds of molecules, and it gets really, really complicated. So we're going to kind of skim over that complicated bit and I'll tell you what we're going to look for. So like I said before, we need star formation and dust grains. So what I did was I looked at a large area of the galactic center and picked out regions that had star formation and dust grains, because that's all we're going to care about if we want to understand cool, rich, organic chemistry. So if you look at this map here, this is called an alpha fit. I'm not going to tell you how it works unless you're very curious afterwards, because it's a pain and it sucks and I hate it. But other than that nightmare, it tells you this reddish orange stuff is all dust grains. So you have a cloud here in space and it has a ton of dust grains in it, which means, okay, cool, check. Now we're going to look at the spectra of that region in general, and I'll get into what that means in a minute. But basically, bright light good, bright light important, that means there's probably star there. There's a lot of energy. That's cool. And look at that. That means there's a lot of chemistry. I'll get into what that means in a minute. But basically, this tells us there's dust grains and there's star formation. We found a region. Cool. Let's go forward with that. So This is the whole galactic center. It's about 1,000 light years across, and this is basically a map of it that's tracing a molecule called carbon monosulfide, just a carbon and a sulfur atom combined together. One of the most common molecules in space, second only to carbon monoxide. And so we use it, as astronomers, we use it to trace pretty much just any region of space with a lot of gas. So if you look at this, basically any of these brighter regions are just areas where there's a lot of carbon monosulfide. Now, let's start orienting ourselves. The center of our galaxy has a supermassive black hole. This is one of the brightest emitting things in our galaxy, biggest black hole in our galaxy, and it's a great way to just kind of orient ourselves on where we are. Next, this is Sagittarius B2. This is the biggest, richest, most complex cloud anywhere in observable space at the moment. We have not seen any cloud anything like this before. It exhibits extremely rich chemistry. It has some of the most massive star formation we've ever seen. And it's just a very interesting dynamic cloud. Scientists have been loving this thing for a long time. They've been looking at it for ages. It has about 10 million solar masses in it, which means about the mass of our star. Imagine 10 million of them. That's about the size of this cloud. It's massive. It's huge. And because of that, again, it has a lot of complex chemistry, and it actually forms stars really quickly. You get about 0.04 stars forming in it every single year, which doesn't sound very fast, but if you think about it on an astronomical scale, these stars last millions to billions of years. So forming one in a couple hundred years tops is pretty fast. But I don't really want to look at this region, and there's a couple reasons why. Again, this is a super rich, complex region. We don't see anything like it anywhere else in space. It's great as a lab. It's great as a simulator to see what kind of chemistry is possible. But it doesn't really relate to the rest of our galaxy. It doesn't really, our star would never have formed in a system like this. It's too big, it's too dense. It never would exist here. However, there are regions in the galactic center that are on a much smaller scale and do resemble galactic clouds that are very similar to the kinds of solar systems where our star formed. So I found one of those called Cloud C. And this one is about 1,000 times smaller than Sagittarius B2, so it's much smaller, but it still exhibits that dust grain and star formation, and it exhibits interesting chemistry because of that. And it's also at a pretty high temperature, 220 Kelvin. So let's have a look at what we can see in Cloud C. My objectives specifically are going to be seeing every single molecule there. I'm just going to define everything. It's going to take a while, but that's all right. That's my main goal. And then I'm going to compare that to the molecules we've seen in Sagittarius B2 and see if there's any similarities. Because this cloud is so much dimmer, we don't really know if we can see everything in this cloud. But if we can show that the chemistry between Cloud C, the small one, is similar or at least very unique or not unique to Sagittarius B2, that means we might be able to say that the chemistry between them is similar enough that they might create these molecules all throughout the galaxy. So that's my second goal. And to do that, I'm going to look for trends in like chemical pathways and then use that to determine if Sagittarius B2 has unique chemistry or not. And this is just a close-up of Cloud C. Basically, it's the same map before using CS to trace it. And you've got this really big bright core. This is the region I'm pulling from. So how am I actually looking at any of this, though? Like, this is 25,000 light years away. That's pretty far away. How do we know what the heck's going on? Well, as I mentioned before, we look at light emission. And by light emission, I mean the field of spectroscopy. So you have molecules, and all molecules are able to reflect light. The reason why this is gray, the reason why the table's brown, is everything emits light at a specific frequency. And that frequency is very broad. And we can use that frequency and that detection, and the detection of that light, to understand what we're looking at. Specifically, these molecules are emitting because they're hitting one another. It's very, very rare because, again, space is pretty empty. But because we're looking at such massive regions, like these are millions of times larger than our solar system, those little minute chances add up. And we're actually able to see some emission. When they collide with one another, these molecules get all excited from that collision, and then they emit photons, and we detect it with antenna. And the reason why this is important is every single molecule actually has its own unique pattern of emission. Think of it as an electromagnetic fingerprint. Everything is completely unique. And so if we can get a broad enough frequency, a broad enough wavelength to look at, we could see more and more molecules, right? Because if they're all unique patterns, if we look at just a broad enough area, it'd be like trying to fish. If you're fishing with a tiny little net, you might catch one or two fish, but if you make it the size of a lake, well, I'm probably going to catch all the fish then. So, for example, we're going to bring back that carbon monoxide molecule. This is a graph of it. So you have intensity on the y-axis, and then you have wavelength, or synonymous with frequency, on the x-axis. And this is what it looks like. Kind of cool, unique pattern. I'm going to basically do this, but I'm going to do it for so long I'm going to want to cry in a hole. So basically, we use interferometric telescopes, which are massive telescopes, billion-dollar telescopes. For example, this Atacama Large Millimeter Submillimeter Array consists of a bunch of different telescopes working together in Chile, and there's about 400 of them working together, and because of their size and scale, they're able to detect a lot of frequencies at once from these really, really large distances because they're extremely sensitive. I actually, for my project, got to visit the Very Large Array down in New Mexico. That's me in front of one of their satellites. They have about 42 of them, which is pretty cool. So I'm going to basically do this where I do pattern detection, but I'm going to do it for a much broader frequency, about 30 gigahertz, which is about 90 million times bigger than that graph right there. So let's see what that looks like. Now, bear with me here. This is going to be fun. What does that mean? I see a lot of lines. So what those lines are is a lot of emission. So again, like I showed before, you have intensity on the x-axis. In this case, I'm measuring it in kelvins. Don't ask me what that means. I'll cry. Not actually, but if you're more curious about it, I'll explain it later on. But it's a long process to define. And then in this case, we have a version of frequency on the x-axis. This way just makes it easier for me to understand what the heck is going on, called radial velocity. So as you can probably guess, these lines represent molecular emission. Each one of these is a molecule. That big one there, that's probably molecule, that's probably molecule, that's probably molecule. But wait. There's like some smaller ones too. So is that a molecule? Maybe. But wait, there's some really, really small stuff that's so hard to see. Could that be a molecule as well? It's really hard to tell. On top of that, I've got another spectra. That's too much. Man, that's a lot of spectra. I don't want to work with all this. I can't do that all in my head. It'd be a really long time and it'd take forever. So we're going to do this more systematically. We're going to take the spectra and we're going to identify it using stuff that other scientists have already done. So there's a group called the Jet Propulsion Laboratory, or the CDMS database, and what these people do is they show how molecules emit frequencies, emit spectra in many, many environments. They simulate it and then they actually experimentally determine it for thousands upon thousands of molecules in thousands upon thousands of environments, and then they put them on this big database for us to look at, which is great because that means I don't have to do any extra work, and I love it. So instead of doing all these experiments by hand thousands of times, which would probably take 50 years, I get to instead borrow their data and use it to interpret what I'm actually seeing. So we're going to zoom in on one line for now. Let's just take a look at a single line. In this case, CS. We talked about it before, carbon monosulfide. We expect this to be everywhere. So we've got that molecule now. Let's import some of the data we understand, and we're going to create a synthetic model. We're going to essentially guesstimate what this frequency would look like based off of how this molecule interacts in real life. And look at that. So it's not quite a good fit, but what I can do is I can then adjust the parameters. I can say, okay, let's make there be a little less of the molecule. Let's put it at a lower temperature. Let's change the size of the source I'm looking at. I mess with a lot of dynamic stuff to basically make it fit the model until the model matches the observed emission frequency. And then I just do that thousands of times, over and over and over again, to try to simulate this. And I'm obviously drastically oversimplifying this process. There's a lot of hyperfine splitting. There's a lot of quantum dynamics that go into how these molecules emit uniquely, and I have to understand all of that. But for now, this is a good basis. So let's see what it looks like when I did all of it. That's awful. That's awful. I have no idea what that means. I hope none of you know what that means, because that's crazy. That is way too much stuff. So, so you guys don't have to. I spent the last 2 months interpreting what the heck all of this means, because it took me about 1.5 years to make this. Basically, what I found is that a lot of the complex molecules observed in Sagittarius B2 are actually present in Cloud C. However, those lines, those things I was using to identify whether something was present, there's about 30% less of them in Cloud C than the big complex Sagittarius B2 cloud. So that means there's less going on, right? Well, not necessarily. So because Cloud C is less energetic, there's actually a decent chance I'm just not being able to see what's actually present because it's just too dim. It's so far away and it's hard to actually observe all this. So what that means is I got to do more work and actually start digging into the chemistry to see how they're related to one another. And there's a couple ways we can do that. we're going to look at the molecular products in Cloud C. That means like some of the most complex molecules we see there, and then compare them to some of the most complex molecules we see in Sagittarius B2, see if they're both present, and then we can use that to determine if the reactions there are feasible in Cloud C, even if we aren't observing the molecules actually. So let's take a look at some of the most complex molecules observed in Sagittarius B2. There's hundreds of them, obviously, but I'm just going to show two because otherwise we'd be here for an hour and a half, and I think y'all would probably attack me. So first we have ethyl cyanide and ethyl formate. These are two pretty interesting structures that are quite useful in basic organic reactions, but they're nothing crazy. However, they're also present in Cloud C. Let's go. So what that means is that it's likely that all the necessary daughter species, all the smaller molecules that it took to react to form this. If you remember, it took like 6 different types of molecules to form dimethyl ether in my first example. That means all of those kinds of structures have to be present to form these two. And since that, even if we can't detect them, that means it's very likely that they're still there. And then I just did that hundreds of times with tons of different molecules, and that basically told me that they're relatively chemically related. Not enough to say that they're exactly identical, but it does show that a lot of the complex organic molecules are present in both clouds. And those are important for a couple of reasons. One, astronomers care because A, it's nice to know what's going on in space. Specifically, they use these molecules to simulate environments, the radial velocity. Basically, they can tell how fast gas is going, what temperature it exists at, how it forms stars, how it forms black holes. They want to know all of that. And understanding how these molecules form and why is really useful for them to do that. But I'm a biochemist pretending to be an astronomer, so I don't really care about all that. I'm more interested in biochemistry-related stuff, the formation of life. So let's take some of the molecules I detected in Cloud C, this environment that resembles a proto-solar system, and see what it's actually capable of forming. So before I do that, though, I'm going to do one more shout-out because my professor really wanted me to talk about some of the cool stuff these molecules can do beforehand. So first, let's talk about some tracers. You have a molecule known as silicon monoxide, SiO. Pretty simple structure, just a silicon and an oxygen atom. Now, this molecule is one of the ones that it can only form on dust grains. However, when it does form, it doesn't release enough energy to kick itself off of said dust grain, so it actually gets trapped in it. So what's really cool is that means if we detect it, that means that those dust grains had to shatter in some way or another, so it released all that SiO. And one of the only things that's capable of doing that is supernovas. And so what you can use is you can use molecules like SiO to trace supernova shocks as they travel through gas and shatter all that dust. And you can do this with dozens of molecules. HC3N is a really good one for tracing temperature. So many different kinds of dynamics you can use. But now, moving on from that, let's talk a bit about chemistry. So, as I mentioned before, you have a solar system, and it starts to form slowly by gases condensing in on each other. You watch it happen as it gets hotter and hotter, denser and denser, and eventually, given just enough time, if it gets hot enough and it happens properly, and just the right amount of gas gets hit together, you get fusion. And fusion results in the formation of a star. And all of a sudden you have a ton of energy being released. It starts to push away excess gas, but also starts to heat up all that gas excessively and allows it to start condensing and combining into things like planetesimals. And they also allow for a very drastic increase in chemistry. So that means you get all these complex structures that we saw before in Cloud C orbiting around a solar system. And it all gets picked up and integrated into these planets as well as asteroids and comets. All the stuff just floating around the solar system is picking up this dust slowly. So let's talk a bit about Hadean Earth and why that matters. So Hadean Earth is Earth about 4 to 4.6 billion years ago, this period when it was just forming and we had a reducing atmosphere. There wasn't oxygen everywhere. It was a lot of CO2, methane, ammonia. And in this atmosphere, scientists found out that it could actually form prebiotics, things like RNA bases, DNA bases, amino acids, all sorts of different stuff necessary to produce life. And so they theorized, okay, well, maybe the atmosphere was forming these prebiotic organics, and then they fell to the surface, mixed with water, and maybe cells did some cool stuff to form life. It's an interesting thought. The thing is, Sarah Horst, this great chemist from Johns Hopkins, recently came out with a study that showed that due to some geologist predictions, water wasn't really available in this era, or at least we predicted that it wasn't for a very long time. And the period by which water eventually was available due to outgassing was a time frame when the atmosphere could no longer produce these organics anymore at an efficient enough rate to create enough prebiotics to maybe build life. So that's caused scientists to look at a lot of other stuff, things like hydrothermal vents, outgassing of like interesting composites, all sorts of stuff. But my project is looking at a bit of a different one, a more extraterrestrial side, seeing if we can deposit a lot of these prebiotic organics due to asteroids or perhaps comets. Now, this is actually a pretty popular theory. Scientists have been looking at it for a while, and what they did was they were able to extract and take samples from a lot of asteroids around Earth, and they found a ton of interesting stuff. They found fatty acids, which are the stuff used to make cell walls. They found RNA and DNA bases of almost every type are capable of forming inside of asteroids. They've also found most of the amino acids. I believe it's 18 of them right now, as well as enzymes like succinic acid, which is essential for the citric acid cycle, one of the most common energy-producing mechanisms we have right now. So that means that you're getting all these really complex organic molecules in asteroids, but we don't really understand, they weren't really understanding how these were forming or where they were coming from. Well, that's where my research came in. If you remember, Cloud C is kind of similar to our solar system. It's one of the brightest ones we can see that lets us observe all this chemistry. So what I was able to was essentially provide an analogous system and show, hey, here's some of the prebiotics and some of the organic molecules that our clouds are capable of producing, which means an asteroid could come along and run through one of these clouds where all these organics exist in a cloud like our solar system. And it runs through and it starts to grab them all up, and then it produces uracil, amino acids, fatty acids, all these different things. And then eventually it collides onto Earth where there was water, and it could perhaps dump a lot of these organic structures, which could then result in the formation of life. Now, that's the end of my talk. I'm going to give a bit of a takeaway section. So again, what we discuss is that organic molecules can be produced in space, a lot of very complex ones, and I detected several thousand of them. So I wasn't going to display them all here. Again, that'd take a very long time. These organic molecules are formed in dense regions of gas such as Cloud C, and because of that, we can set that system to be analogous to something like the beginning of our solar system, and thus protostars could be exposed to these organics and let things like asteroids pick them up and potentially deposit them onto our surface. Pretty cool stuff. Obviously, this work has a really long ways to go. Scientists have been working on this for like as long as we can remember. Everybody has a lot of curiosity to it. I'm just like one little piece to the puzzle of it, but I'm glad I got to contribute. I wanted to thank my research advisor, Dr. Mills, for letting me get into this. She's the one who's I got to present at Harvard for this research. I've got to travel all over the country. It's been an amazing thing. I've really enjoyed this project. I also wanted to thank Sarah for helping put all this together and helping me with my slides. She helped me change them a lot. It looked great. I wanted to thank the Ad Astra Kansas Foundation for obviously giving me money and bringing me here. We love it. It's so helpful. I wanted to thank my parents and my grandmother for help getting me interested in science and inspiring me to do it. It's been a lot of fun, and I'm glad I got to learn from you guys. It's been so helpful, having your support. It's made it a lot easier to go through college. And then lastly, I want to thank all you guys for showing up here and listening to me yap for a while. And yeah, any questions? Very true. Yeah.
The asteroids that were found to have some of these organic compounds. How do we know that those compounds were from space, or how do we know whether it hasn't been contaminated with?
So that's a great question, and there's actually a lot of processes that they use to ensure this, and they actually have a whole system to specifically out these kinds of molecules if not. So first, they have to very specifically isolate these asteroids, and then they use something called HPLC, or gas column chromatography. And what those do is that basically identifies all the molecules within this region. They keep this thing almost completely isolated. They extract the sample, and then they put it through this column that's been purified a ton of times to see what's there. And then afterwards, they have to look at a lot of these structures and see, okay, is this feasible to exist in this region, in this asteroid? Would this be possible? And if it is, they base that off of a couple things. One, they look at where they detected where the asteroid landed, or if they got it from space, they looked at where it was in space, and then they made sure to check what molecules were on all their tools and all their instruments while they were collecting this. And basically, if that molecule was on an instrument and it also showed up in the sample pretty continuously and synonymously, they would cancel out that molecule. Any other questions? Yes.
So you're looking at, what was it, area C?
Cloud C, yeah.
Cloud C. That's 25,000 miles away.
Yes.
So the space in between us and that's not completely empty.
No, it's not.
How does that affect the emissions that you're seeing from Cloud C?
Very drastically, and it's very fun trying to deal with that, and it's a lot of math. So there's a couple of ways you can deal with it. One, so as you said, there is plenty of stuff in between, especially stuff like carbon monoxide, carbon monosulfide. You'll have, let's say you have a source here, it's emitting towards us, and then there's a cloud in between us. That cloud is doing two things. One, it's absorbing the emission, so it's reducing it. It's making it harder for me to know what's there. And then secondly, it's also emitting, which means that it's messing with my data even more. And it's saying, I'm also here, deal with me. And so to resolve that, there's a couple things we have to do. First, there's a lot of really complicated math you can do to cancel out. So I don't fully know how all of it works because computer does most of that for me, but it cancels out some of the excess energy and clears up noise. The second thing you do is what's known as radial velocity. So all gas in like the galaxy is moving at speeds. The whole galaxy is rotating, correct? So if we're looking at the galactic center, it rotates at a very specific speed. Specifically, the one I'm looking at rotates at about 37.8 kilometers per second. That's cloud C. Now, if I'm looking at a gas cloud that's, say, halfway between us and the galactic center, it's going to be moving at a very different speed, much slower or perhaps much faster, anywhere from 200 kilometers per second to, like, say, 10 kilometers per second. If it is outside of a very specific range, for me, I believe it's about 37.8 to 39.2-ish, I believe. I'd have to go look at my data again. But if it's within that range, I can count it as potentially being from that region of space. Otherwise, if it's outside of that, I just completely ignore it. Yeah?
Okay, now you were talking about asteroids entering our atmosphere and
Yes.
colliding with Earth.
Yep.
Are they actually putting life-forming chemicals in the Earth when they collide on the Earth? Or?
So we're not entirely sure yet, and scientists are still studying that. So that's so what we discussed with that is called accretion rates. Basically, as an asteroid collides to a surface of a planet, we need to know, is it soft enough of a landing to destroy everything inside of it? And there's a lot of papers that argue that some do, and there's a lot of papers that argue that some don't. It really depends, and obviously asteroids are very dynamic. You could have a certain size, if it gets too large, it could all like get destroyed, or perhaps if it's too small, it could get destroyed, but there might be a Goldilocks zone where it doesn't destroy all the molecules within said asteroid. And I can't quote the papers off the top of my head as to that exact size, but as far as we know, there are a couple that are able to accrete onto the surface of a planet without destroying all the like precious organic molecules in the interior. They essentially get shielded when it collides because it's thick enough. That's the basis of that. Wow. Yes.
Have you had any observations that like really surprised you, like things you didn't expect to find or things that you expected to find that weren't there?
Yes. So there's a molecule called deuterium. It's basically hydrogen with an extra neutron onto it, which makes it a little heavier. It's a very rare molecule in the galactic center. We don't really know why it is, because it should be relatively common given hydrogen's pretty common throughout the galaxy, but we just don't see it in space very often. And we saw it in Cloud C, and we didn't see it in Sagittarius B2, which was very, very unusual, and we do not know why that is yet. And I'm actually talking to some people in Madrid, Spain, the Center of Astrobiology up there, to try to figure out what the heck is going on. Anything else?
Yeah, when you were collecting the data, how long was the duration of you?
Of the observation?
Yeah.
So I'm a part of this amazing organization called ACES, the Atacama Large Millimeter Submillimeter Array Central Molecular Zone Survey. Long acronym name, but basically these people are the leading experts on the galactic center, and they gave me a lot of data. So I got about 4 hours of observation time across multiple days to do it. And yes, you do have to account for that because the planet's spin is very different and the rotation of the galaxy is very different, and it's a lot of very annoying, complicated math. Yeah.
So you talked about that you work with Madrid, you talked about data from Chile.
Yeah.
So being from Kansas, and we got a good school, but we're still in Kansas. How do you feel, how much is it Kansas reaching out to these other groups? How much do these other groups support Kansas? How does that dynamic work?
So to clarify this, are you talking about just like trying to do science in general, like building like collaborations between different groups? Are you saying like because Kansas is so isolated, like like Kansas needs to do more work reaching out, or what do you
You said
mean?
you're working with not just here in the US, but
Yeah.
with all these groups, so how is that support network, how did?
Oh,
you
yes.
reach out?
Okay, I see. Yeah.
You reach out to them, do they come to you?
It's kind of a mix of both. So the nice thing about being a professor I'm not a professor, but the nice thing that I've seen with that is you do a lot of travel to local conferences where a lot of people in very similar fields present all their work together. And because of that, you all get to meet up and have a little powwow and talk together and be like, you're on an interesting project that I'm curious about. And they network with each other to start building these bigger and bigger collaborations. And I just happen to be a part of a really large one that's been building up over the past like 30 years. And as like time goes on, you meet more and more people from broader and broader regions across the world who have an interest in the same topic, and you all slowly start to work together more and more. And as your group gets bigger, the government gives you more science, and they give you more like time to work with like telescopes, which is great. They give you more money, so it's very beneficial to work in these bigger collaborations as you get more time from people and you get more respect generally too. So they just naturally sort of develop over the years. And honestly, being in Kansas isn't an issue with that because, again, you're traveling to conferences, continuously doing research, so it really hasn't been much of a limitation. Any other questions? Yeah.
Yes, the James Webb Telescope is conducting a lot of research in the same area of imaging exoplanet atmospheres.
Yep.
Spectroscopy. Are you able to have access to some of that recent research and follow some of the Webb Telescope imaging, especially regarding the galactic center?
Yes, actually. So there's a couple of problems with the James Webb Telescope for my research specifically. The galactic center is just on the horizon of our planet, and so it's very hard, even with the James Webb Telescope, to get observation time for it. It's a very limited window across the span of a year, so it's a very, very popular thing. So me being an undergraduate, I don't really get access to a lot of that cool data, but it just so happens that my professor's husband, Dr. Ian Crossfield, he's an old professor from MIT, and he works with the James Webb Telescope looking at exoplanets, and he does have some observations of the galactic center, and it's very nice being able to collaborate with him and getting to see how it works. The James Webb mainly works in microwave to infrared range, whereas I work in the radio wave, which is much, much further away, or much, much further down in the radio electromagnetic spectrum. It's generally more useful to use radio for me particularly because it ignores more of that intermediate gas in the way. And almost everything emits in an infrared spectrum, almost everything emits in the microwave spectrum to some capacity, but it's harder for like a lot of gases to emit in the radio spectrum, and it lets it pass through all this stuff in the way. It doesn't get absorbed, and it's a lot easier to see. But there are people using the infrared spectrum to look there. Anything else? All right, cool.